Hi guys, this is Sampling Distributions Part 2. So in this video we're going to be talking about the sampling distribution of the sample proportion. But before I get into that, and I want to make sure that, again, like we were doing before, I want to make sure that you have a really good intuitive idea of what that means. At the end of Part 1, which was sampling distributions of the sample mean, I gave you a question. Just to tide you over, I said, hey, let's propose that we have this situation. We have a distribution with a mu of 30, that's a mean of 30, and a standard deviation, sigma, of 15. Let's imagine that you're taking samples, lowercase n, of size 36. So, what score, meaning in this case, what sample mean would have a z-value of 2.8. How are you going to solve that? Okay, well, just to finish up that question from Part 1, what we're going to do is remind ourselves of what the formula for z-scores in the context of the sampling distribution of the sample means is. And I gave you more than one version. I think this is one of the versions I gave you during that video. So like many things in math, one approach is, well, gee, I have a formula where I have everything that goes into it except for the one thing that I'm solving for. So let me just solve for that one thing. That's an approach, and we can do that. Remember, we have the 2.8, the z-value, but we're solving for the sample mean that would yield that. So I'm going to go ahead and just fill all that in. Let's do that. So I have 2.8 must equal whatever sample mean that would give me that in the end, minus mu sub x bar, let's be correct, divided by sigma divided by the square root of the sample size. So we can work that out fairly easily. 15 divided by the square root of 36 is 15 divided by 6. And a little math on your part, you're going to find that that's 2.5. This is just algebra. I'm going to multiply both sides by 2.5, and I get, let me make sure I'm staying within camera, 2.8 times 2.5. This is the next step after this. I've multiplied both sides, and that must equal x bar minus 30. Well, 2.8 times 2.5 is, let's see, that's 7. So we have 7 equaling x bar minus 30. It's a simple matter to add 30 to both sides, and we've solved for what x bar must be. It might feel more familiar to you if you put x bar on the left and 37 on the right, but it doesn't really matter. The equals, remember, in math is telling us that those two objects have the same valuation. So that's the solution. Okay, let's get into the sampling distribution of sample proportions. Okay, so let's talk about the sampling distribution of sample proportions. I'm going to give you rules that govern it, and I'm going to talk about it a little bit, but before that, let's just make double sure that everybody's got a good, intuitive idea of what this thing is and what it does. Well, look, you probably suspect already that we're going to be working towards some sort of distribution, which is a normal distribution. But how do we get there? Again, let's imagine taking every possible sample from a population. And just like we did with the sampling distribution of sample means, we have to imagine a lot. I mean, in general, for a given sample size of lowercase n and a population size of uppercase N, you're talking about big N choose little n numbers of different samples. If that isn't clear to you, what I mean, message me or send a comment at the bottom and I'm going to answer you, okay? It's not that important for you to understand that at this moment. But that's going to be the number of samples possible of some given size from some population size. Point is, right now, huge number. So we're imagining all of them, and we're going to take those samples, just like in part 1 of this video series, the sampling distribution of the sample mean. We're going to take all of our samples in our minds, we're visualizing this or proposing this theoretically, and we're going to take the results of those samples and graph them. And those sample results will form a normal curve. But what are those sample results? We're talking about sample proportions now. So when we're talking about sample proportions, we're really talking about binomial decisions. Did you like that new movie? Yes or no? We're taking a poll. Do you support the new law that they're proposing? Yes or no? Do you favor the new subway rules that restrict ridership between 1 and 4? Yes or no? We're taking samples of something which is a binomial question. Up or down, better, worse, hot or cold, yes or no, support, doesn't support, and so on. And realize that when you take a sample, you're going to get a decision that falls along a binomial axis, just to be a little pretentious about the way that we talk about it. So you don't really, within each sample, get a distribution in the form that you're probably thinking of them, right? Mathematicians would still call the results of a poll like this a distribution, but it's not really something you can easily put on a curve. It's just a proportion. 52% for, let's say for example, purely randomly chosen. 52% for, 48% against, for example. But the point is that under the right circumstances, which we're going to go over, you take all the many samples possible and you poll them and see what results you get, and the results themselves will form a normal distribution. Sometimes this can be kind of counterintuitive in the way that it works, but it really works that way. We're going to go further with this. Okay, so I want to go into this a little bit further to get a good idea of what we're talking about, and also to share some of the oddness, because some of this is really interesting and counterintuitive. Let's imagine a population. Now, I naturally draw a normal distribution, but we're really talking about a population that's split on some question. So you know what? I'm going to redraw that. I'm not even going to restart the video and eliminate that. Let me just redraw that. Here's our population. This is everybody in a given city, or everybody in a state, or locality, or club, or some other entity that incorporates people, and they're going to vote. Okay, it's the Academy, and should the new movie win an Academy Award? Well, it's not a very good movie, or it's not very popular. So we have a predominance of people saying, no, the new movie sucks. We don't like it at all. 65% said, no way. 35% of the Academy likes the new movie. Okay, let's imagine that this is a big academy. Now, I have no idea how many people are actually in the Academy of Arts and Sciences in Hollywood. I have no idea. But let's imagine that it's some big number, 1 million people. I'm sure that's much bigger than the reality. And we're going to go through and we're going to take samples, and we're going to visualize taking samples of some reasonable size, right? So out of 1 million people, we're going to be taking samples of 1,000. In fact, we're going to take every potential separate and distinct sample of 1,000. Now, please realize what's going to go on. We have 1 million people here, and we're taking samples of 1,000, so 650,000 people don't like the new movie. It stands to reason that we're going to get a bunch of samples which are like 0 yes, 100% no. Even though that's not the natural distribution of the overall population. 650,000 people don't like the movie. We're only taking samples of 1,000, which might be big enough to give us good results as pollsters, depending on how much precision we want, and everything else. But nevertheless, I think it's easier for you to imagine we're going to get a bunch of samples that show absolute failure of support. 100% of a bunch of those samples show zero support and 100% against. Keeping this in mind also, we're going to have 350,000 people that like the new movie. They are in the minority. But it doesn't matter. 350,000 people is enough so that if we're taking samples of 1,000, we are inevitably going to get samples where 100% likes the new movie and 0% doesn't like the new movie. So you can imagine that there are going to be samples at both ends of the spectrum. And then, of course, you're going to get a large number of samples that show the expected result. Now, that's going to be actually the largest subtype of samples that we're going to be getting, but we're going to see all of those types. We're going to see proportions of 20% for and 80% against. We're going to see proportions of 80% for and 20% against, and every sort of mixture that you can imagine. In fact, it's going to be a spectrum going from 100% support down to 0% support and 0% opposition up to 100% opposition. You are going to get results all along that spectrum in this scenario where we have a population that's big enough and a sample that's sized appropriately. Okay, so here's the point that I'm getting at. It's really strange, really interesting. We have a distribution that is kind of sort of more or less 2/3 against, 1/3 for. It is not symmetrical. It is way not symmetrical. What do you think is going to happen to the distribution when we plot all of our sample results, all that spectrum of sample results that I just spoke about? Well, it might seem counterintuitive, but under the right circumstances, and those are fairly easy to achieve, we're going to get a symmetrical distribution. Very strange. A symmetrical distribution where 50% of our samples are opposed and 50% of our samples are majority for. The mean is going to be P. Now I'm going to use that letter to represent the proportion of support or opposition in the entire population. What I mean by that is P is actually going to be, let's say we're talking about just support in the Academy for the new movie. So P, and by the way, this replaces mu in the distribution of sample means, mu sub x bar. This kind of fills the same role. If we're talking about support, then P, the population proportion for support, would be 35%, as we just talked about. I hope this is making sense, guys. I'm going to write it as a decimal also, 0.35. So that's the mean. And even though it's not 50%, we still have a mean of 0.35 and a symmetrical distribution with values ranging less than that on the left and greater than that on the right. Completely counterintuitive, but that's the way it is. So we're talking about a graph that is a graph of all the many sample proportions. I'm making this idea up as I go along. We're talking about a graph that shows support within the Academy of 1 million people for some new movie. And we decided that the Academy really supports the movie only to the tune of 35%. So we go out and we take all the samples we can think of. We take a sample from this group of 1,000 and that group of 1,000 and every one possible. And we take a look at the amount of support that we get within each of those individual samples. Let's say in one particular case, we get a result of 40% support. I'm using decimals right now. We would call that as a result of a single sample p hat. So in terms of the way to write things out, right? P hat is the proportion of some given sample. Big P without the hat is the population proportion for whatever it is that you're trying to measure. Well, again, I may be, belaboring this point way too much, but actually that's okay because I want to make sure it's super clear. We're talking about a distribution of sample proportions where each individual sample is just a proportion of support or opposition or whatever other binomial question you want to investigate. And we're graphing all the potential samples possible in a given population. And when we graph them, despite the asymmetry of P that exists within the parent population, assuming we follow certain rules, again, coming up on that really soon, assuming we follow certain rules, it's still going to result in a symmetrical distribution. In fact, not just symmetrical, but normal. Okay? In terms of visualization, this thing is made of all the many P hats. Just like a normal distribution is made up of scores, I showed you that at the beginning of part 1, and the distribution of sample means is made up of all the many means of all the many possible samples. I showed you that in the middle of part 1. Here we're talking about a distribution that's made up of all the many possible samples, their proportions. So to the right of the mean, you have proportions that are greater than the population mean, in this case of 0.35. That's why this would be over here. On the other hand, if you had a proportion that was something less, it would end up over here. And we span the whole spectrum from 0 support to 100% support. Somehow this thing still ends up being symmetrical. We could really study this for ages, but just like with the sampling distribution of sample means, where we had 4 rules that I wanted to show you guys here, I'm going to show you 3 rules that are central to the distribution of sample proportions. Like I say, there's so much, we could just go forever with this stuff, but here's the main core of what you gotta know. 3 rules. Here's the first rule. 1. The mean of the distribution of sample proportions, which incidentally is mu sub p hat. Again, that's kind of descriptive, isn't it? It shouldn't be confusing. It should be clarifying for you because it must be the mean of a distribution. It says mean, and what is it the mean of? It's the mean of p hats. So the mean among all the p hats, the sample proportions, is equal to big P. I kind of assumed that that would be intuitively understandable already when I did the last segment of this video. And it should be clear enough from the way that I talked about it. I think it's digestible intuitively. The mean of that distribution of all the p hats is just the population proportion anyway. And it makes sense that it should be so because each individual, let's remember those 1 million people in this theoretical academy that I'm imagining, each one of those million people expresses their opinion once to give us P. But they express their opinions in equal amount once. Now, if we're thinking about the mean of all the sample means, again, we're in a position that everybody's contribution to the overall opinion is again equal. It's just that this time, in the middle of that distribution, they are doing so through the mechanism of all the many sample proportion procedures, let's call it, that they're participating in. So mu sub p hat, which is the center of the distribution for distributions of sample proportions, is equal to the population proportion in the parent population that it came from. Second rule, the standard deviation of the distribution of sample proportions, sigma sub p hat. Again, we're still following the same pattern. With distribution of sample means, it was sigma sub x bar. Now it's sigma sub p hat. So that we can see that as suiting our expectations. Well, okay, what is it? It's going to be the square root of the following construction. It is p, the population proportion, times 1 minus p, its complement, divided by n. Please notice that this whole fraction is underneath the radical. So p times 1 minus p divided by n, then the square root of the whole thing taken, and that is the standard deviation of the distribution of sample proportions. Again, this is theoretically exactly correct with an infinite population, but it's actually very close and treated as, you know, a formula not to question. Let's put it that way. As long as your sample size is less than or equal to 1/10 of the population size, and then it's going to work just fine. Now, I want to point something out. It's easy to confuse this standard deviation formula with the standard deviation formula of the binomial distribution. Do you remember what that is? I didn't talk about it in my binomial distribution video because we didn't really need to then, and I wanted to keep it a little bit simpler. But you may know from other sources you're reading or whatever that the standard deviation of the binomial distribution is n times p times 1 minus p, also underneath the radical. And they look similar enough so that I gotta caution you as a stat student, do not confuse them, or else it's just an unforced error. You're gonna lose points for no reason, and that's not cool. You can derive this from that fairly easily. And for a few of you guys, the mathematically minded, maybe the math nerds, it's going to help you to remember why one is one and the other's the other. Let's take, I'm going to put it right here. This is the standard deviation of the binomial distribution. It's in the reading. And we're going to say to ourselves, well, what does this represent? We're going back a few videos. This is, within a group, the number of people or individuals or whatever that achieve a success. So we might think about how many heads do we get in 10 coin flips or something. That's something like, I think, what we did in that video. But that's a raw number. It's actually a frequency, remember. It's not a relative frequency. It's a raw number. It's not a proportion. So if we were to say, for example, how many heads do I get in 10 coin flips? If I got 7, that would be a frequency, a raw number. But if I want a proportion, I'd have to divide by n. So 7 heads in 10 coin flips becomes a proportion when I divide it by the 10, the number of coin flips. That's really just n, isn't it? It's my sample size. So what I can do is I can say to myself, this gives me a standard deviation of a raw number. I'm going to turn it into a standard deviation of a proportion by dividing by n. Well, that's fairly easy. What happens when we move 1 over n into the radical to work upon this expression? We get this. Let me erase. We're going to get radical 1 over n squared, aren't we? We had to move that inside, and for it to retain the same value, we squared it. It's 1 squared over n squared moving inside the radical. And that's still multiplying n times p times the complement of p. By the way, depending on where you look, if you look for supplementary materials or whatever else, it's really common. In fact, the way I learned it was not to call this 1 minus p, the complement, but rather to call it q. So that's super common. It means the same thing. Well, you guys are already seeing what I'm doing here, I think. This n, which is not in the denominator of a fraction, it's just n, that's going to cancel with the squaring of the n from the 1 over n that we brought inside. So look at what we have. If I simplify this, I have literally, let me squeeze in, p times 1 minus p over that n multiplying the 1. And that's the formula for the standard deviation among sample proportions. So very easy to derive one into the other. And actually, you can do the same thing working backwards also. I'll leave that for you if you want to try that out. It's a good exercise, and it's interesting, and that's one reason why I'm putting it here. But the main reason I'm putting it into this video is because I really want to cement and highlight and make a big point about don't confuse them, please. This is the standard deviation of the distribution of sample proportions. So it's got to have a proportion inside, right? Okay, we'll continue with more stuff. Okay, more stuff. Third rule. When n is large, what does large mean? We'll answer that question. And p is not too close to 0 or 1, the distribution, I'm going to abbreviate it a little, distribution of p hat, meaning the sampling distribution of sample proportions, is approximately normal. I'm going to go like this to represent approximately because I got tired of writing. Okay, so when n is large and p is not too close to 0 or 1, the distribution of sample proportions is approximately normal. Again, almost too vague for us to use, so let's talk about what that means, okay? And this is something central. Even though it's starting out vague, let me point out to you that this is something that you should understand well. We need to have a set of rules that tell us when this distribution is approximately normal, meaning close enough to normality that we can treat it as normal. And even though this rule is vague, we are going to utilize a specific rule as our litmus test. And here's that specific rule. We need for these two rules to be true. N times p, meaning the sample size times the population proportion, must be equal to or greater than 10. And as well, n times 1 minus p must be greater than or equal to 10. Bear in mind that whatever we consider to be p, the thing that we're seeking or investigating or defining as a success, it's almost arbitrary. If I'm interested in people that support this new terrible movie, somebody else might be interested in people that oppose it. So their 1 minus p is my p, and my 1 minus p is their p. That's an unclear way of saying whatever they consider to be failure, I might consider success, and vice versa. So if the distribution is not normal for me, then it's not normal for them either. Let me get to my point, and I'll say it clearly. If you're evaluating a scenario for normality, check both. Okay, really sneaky thing that stat teachers can do. They can make it seem like something's normal because they know that a student will check one rule but not check the second one. You got to check both, okay? I'll give you an example. Let's take a scenario in which our population proportion is 0.7. Okay? And we're going to take samples of size 30, let's say. Now, don't get overexcited about the number 30. That has a special significance when we're talking about the distribution of sample proportions, but not necessarily here. I'm just using the number as an example. So let's go ahead and see if, in such a case, the distribution of sample proportions, all possible samples of size 30, if it would be normal. So I'm going to multiply n times p. So n times p must be greater than or equal to 10. So I have 30 times 7, and I get 21. Great. Now, strange thing, I'm a fairly experienced stat teacher. I will notice that I'll explain this in class, and still students will miss it on a test, right? Be really careful about this. Be thorough. It's much faster to be thorough and secure in what you're doing than nervous and wondering. So in a testing situation, check both this and its companion rule. Let's see if this is true. We would have 30 times, you already see what's happening, but I'm just using this as an example. 30 times 1 minus p, which would be 0.3, and oh, lo and behold, no good. So this distribution would not be normal. We couldn't guarantee it to be normal. Okay, so let's describe some sampling distributions. I'm going to propose that we have a population with a population P of, let's make it 0.45, and we're going to take samples of 100. Now, just like with sampling distributions for the sample mean, if you're describing a sampling distribution, you're going to need to come up with a couple of basic things. You're going to need to come up with the mean of the sampling distribution. In the case of the sampling distribution of sample proportions, it's mu sub p hat, the mean among all the sample proportions. The standard deviation is sigma sub p hat. That's the standard error. We still call it that. And we're going to have to address the topic of normality. Well, that's easy enough right away. Let's do that. We're going to go back to front. I think you see that if we take n times p, that's going to be 45, and that's certainly greater than 10, so we're okay on that front. I'm not going to take anything for granted, because I don't know about you, but when I'm taking a test, usually I'm capable of any mistake, no matter how silly. So even if I think it's obvious to myself, I'm going to multiply n times 1 minus 0.45, that's 0.55, and I get 55, which you got to trust me, I did on paper before I started the camera again. So I see that that's greater than 10, and I'm all set. We're completely normal. So now that just leaves us to arrive at the mean of the distribution and the standard error. The mean, again, that's a calculation that's not even a calculation. It's 0.45. The standard deviation is a little bit more work. You should have the formula with you from moments ago in the video. So I'll just rewrite it anyway. Square root of p times 1 minus p over n, which in our case is going to be the square root of 0.45 times 1 minus 0.45 over 100. Go ahead and try that on your own. I got, and I rounded quite a bit, 0.049749. It keeps going, but that's where I stopped. So that's 6 decimal points. Make sure you got the same thing. Let's do another one just to practice. And this will be a little bit more relevant to current events. Let's say we have something that we're testing for. You either come out positive or negative, and we suspect that the population proportion for positivity is 20%. I wonder if you know exactly what I'm referring to. I'm talking about coronavirus in New York City. As of today, they think that something like 20% of New York City is infected. So we're going to take samples of 800, and we're going to describe the sampling distribution. So let's go ahead and do that. Remember, 3 topics. Mu sub p hat, and that's going to be 0.20. Sigma sub p hat, the standard error, that's going to be radical 0.2 times 0.8 over 800. Okay, and we're going to address normality. So when I work that, I got 0.01414. Actually, just for the heck of it, 2136. So that's the standard deviation of the sampling distribution of sample proportions. In other words, the standard error. So now we have mu sub p hat. We have the standard error. Now we have to address normality. I think it's pretty clear that this thing is normal, but let's just do it the right way. A lot of times in math and science, you have to prove the obvious, because whether it's obvious or not, until you prove it, it's unproven. And that's the attitude. And you got to be like that, because a lot of times you'll be surprised. This time, I'm not sure we will, but we're going to prove it for proving's sake. So I'm going to take n times p, and I get 160, okay? So definitely we're over 10. Now, if you're thinking ahead and you're a little bit sharp with this, I think it's a permissible shortcut to say to yourself, well, n times 1 minus p, n times the complement is just going to be the complement. So 800 minus 160 is going to be some nice number, 640. And you can go at it that way also. That's greater than 10, so we're all set. Thumbs up. We have normality in this particular case. So we can go and test for coronavirus antibodies with samples of 800 and be assured that in doing so, we're going to be operating within a framework of a sampling distribution that would be normal. Okay, so that's part 2. Next, we're going to move on to part 3. Don't go yet. I'm going to give you a question that's going to tide you over until we do part 3. And it's going to be sort of apropos to what we were just doing. If you understood the math that we used to describe the sampling distributions, then this should be no problem for you. Let's imagine, let me just add a caption, but first, there's more. Let's imagine a population whose p is 0.98. 98% of this population engages in something or belongs to some category. We want to do a study of them, and we want a sample size sufficient so that we can operate within a framework of normality in our sampling distribution. So I want you to tell me, what must n be for normality? I'm going to abbreviate. In order to achieve normality, what must n be in our sampling, our sample size, to achieve normality in this situation? And you can achieve normality. You can achieve normality with a proportion of 0.9998 if you want, or even higher. So you can always achieve normality for any proportion less than 1. In this particular case, I want you to tell me, how big does the n have to be in order to achieve normality in this situation? It's kind of an interesting question that I like. So go ahead and like and subscribe, and I'll see you for part 3.